Right now, as you watch this, the entire universe might be sitting on the edge of catastrophic collapse. Not in billions of years, not from heat death or cosmic expansion, but instantly, without warning, at the speed of light. There's a possibility, small but non-zero, that the fabric of reality itself exists in what physicists call a false vacuum state. A temporary configuration that feels stable but isn't, like a boulder perched on a cliff edge, waiting for the slightest nudge to send it tumbling. If this is true, then somewhere in the cosmos, right now, a bubble of true vacuum could be forming, expanding outward at light speed, rewriting the laws of physics as it goes, destroying every atom, every star, every galaxy in its path, and we would never see it coming. The physics is real, the mathematics is sound, and some of the world's leading physicists believe this represents the ultimate fate of everything that exists. What if I told you that our universe might be metastable, that existence itself is temporary and the clock is already ticking? That the very properties making life possible could be the same properties dooming us to inevitable annihilation? Today, we journey through evidence that challenges everything we thought we knew about the stability of reality itself. The story begins in 1977 at a blackboard in Cambridge. Sidney Coleman and Frank Luccia were working on quantum field theory, the physics governing the fundamental forces of nature. They were investigating whether the vacuum of space, thought to be the lowest energy state possible, could actually be something else, something temporary. What they discovered would haunt physics for decades. Coleman and Luccia found that quantum mechanics permits something extraordinary. The vacuum of space could exist in multiple energy states. If our vacuum isn't in the absolute lowest possible energy configuration, what physicists call the true vacuum, then we're living in a false vacuum. The mathematics showed something terrifying. A false vacuum is metastable. It appears stable, like supercooled water that's liquid below freezing. But introduce the right catalyst and everything changes instantly. Let me give you an analogy that captures the stakes. Imagine a ball sitting in a shallow valley on a hillside. It's stable there, not rolling, seemingly safe. But there's a deeper valley further down the hill, the true lowest point. A small bump separates the ball from that deeper valley. Normally, the ball lacks the energy to roll over that bump. It stays put. But quantum mechanics introduces a twist: quantum tunneling. The ball doesn't need to roll over the bump. It can tunnel through it, appearing spontaneously on the other side. This is our universe. The ball is the vacuum state of space. The deeper valley represents a lower energy configuration, the true vacuum. And quantum tunneling means that at any moment, without warning, a patch of space could spontaneously transition to that lower energy state. When that happens, the consequences would be absolute. If you're enjoying the video, feel free to tap that like button. It shows me this content sparks something in you. And if you'd like to stay close as new stories appear, subscribe to the channel. It genuinely means a lot and helps this place grow in the right direction. Thank you for being here. Coleman and Luccia calculated the process in detail. First, a tiny bubble of true vacuum forms through quantum tunneling. This bubble could be smaller than an atomic nucleus. Inside this bubble, the laws of physics are different. Particle masses change, force strengths alter. The fundamental constants that govern chemistry, nuclear physics, and gravity shift to new values. The unclocking wall expands outward at the speed of light, not near light speed, exactly light speed. This means there's no warning, no way to see it coming. The wall would reach us traveling at the same speed as the light that might warn us of its approach. As the wall passes, it converts false vacuum to true vacuum. Every atom it touches gets restructured. Electrons, quarks, the forces binding them together, everything changes according to the new physical laws. The energy difference between false and true vacuum gets released. Coleman calculated this energy release could be enormous, enough to essentially vaporize matter as the transition wave passes. But here's where it gets truly strange. The transition doesn't just change the physical constants, it fundamentally restructures space-time itself. The bubble interior exists in a different vacuum state, which means it has different vacuum energy, what we call the cosmological constant. General relativity tells us that vacuum energy curves space-time. Different vacuum energy means different curvature. The bubble's interior could have radically different gravitational properties than our current universe. Inside the bubble, the universe might recollapse immediately into a big crunch, or it might expand exponentially, tearing itself apart. Or it might settle into a new configuration where atoms can't form, where nuclear fusion is impossible, where life of any kind is unthinkable. The calculations show that most possible true vacuum states would be hostile to any form of complexity. No chemistry, no stars, no galaxies, just elementary particles in a featureless void governed by alien physics. This discovery raised a question that still haunts cosmology. Is our universe stable? Physicists soon realized that answering this question requires knowing the exact values of fundamental constants, particularly the Higgs field. The Higgs field gives particles their masses. If the Higgs exists in a false vacuum state, then everything depending on particle masses exists in a false vacuum state, which means everything. But the evidence forces us to confront an uncomfortable possibility. Measurements of the Higgs boson suggest we might be living on the edge of stability, in a universe that could, at any moment, undergo the ultimate phase transition. The first real evidence came on July 4, 2012. CERN's Large Hadron Collider announced the discovery of the Higgs boson, the quantum excitation of the Higgs field that permeates all space. Teams at the ATLAS and CMS detectors had been smashing protons together at energies of 8 trillion electron volts, and they found it, a new particle with a mass of approximately 125 billion electron volts. This mass measurement was precise, 125.1 GeV, with an uncertainty of just 0.2 GeV. That precision mattered, because when physicists plugged this value into their calculations of vacuum stability, they found something disturbing. Scientists discovered that the measured Higgs mass places our universe in what they call the metastable region. Here's what that means. The stability of the vacuum depends on the relationship between the Higgs mass and the top quark mass, the heaviest fundamental particle. These two values determine whether the Higgs field sits in an absolute minimum, stable, a local minimum, metastable, or no minimum at all, unstable. The measured values put us right on the boundary. With a Higgs mass of 125 GeV and top quark mass of 173 GeV, the Higgs field exists in a shallow valley with a much deeper valley somewhere below. In 2013, researchers at CERN published calculations showing that the instability scale, the energy where tunneling becomes likely, sits around 10 to the 11 billion electron volts. That's about 100 billion times higher than the energy of the Higgs boson itself. This means the false vacuum is protected by an enormous energy barrier. Quantum tunneling through it is possible, but extremely unlikely in any given region of space at any given time. But this represents just one piece of a much larger puzzle. In 2014, physicists at the University of Southern Denmark calculated the rate of vacuum decay for our universe. They found that given the measured Higgs mass, a vacuum decay bubble could form spontaneously somewhere in our observable universe with a probability of about 1 chance in 10 to the 100 years. To put that in perspective, the universe is currently 13.8 billion years old, about 10 to 10 years. The timescale for vacuum decay is 10 to 90 times longer than the current age of the universe. This sounds safe, except for one crucial detail. We're not alone in the universe, and we're not passive observers. High-energy events, cosmic ray collisions, black hole mergers, the Big Bang itself, could potentially trigger vacuum decay. Not by providing energy to roll over the barrier, but by creating conditions where quantum tunneling becomes more likely. The most remarkable discovery involves the early universe. Cosmologists realized that during cosmic inflation, the period of exponential expansion moments after the Big Bang, the universe's energy density was enormous. Energy scales reached values that should have triggered vacuum decay instantly. Yet here we are. The universe didn't collapse into true vacuum during inflation. This puzzle has led to several interpretations. First, perhaps the inflationary field somehow stabilized the vacuum temporarily. The high energy conditions might have actually raised the energy barrier, making tunneling less likely. Second, maybe we got lucky. With only one universe to observe, we can't calculate probabilities. If vacuum decay was possible but unlikely during inflation, and we happen to exist in a region where it didn't occur, then that's the only universe we could ever observe. Third, and this is where things get really strange, perhaps vacuum decay did occur, and we're living in the bubble. Now we venture into territory where observation meets theory in unexpected ways. In 2015, researchers at Harvard discovered something troubling about the Higgs field's behavior at high energies. They calculated how the Higgs self-coupling, the way the Higgs field interacts with itself, changes as energy increases. Below energies of about 10 to the 10 GeV, the Higgs self-coupling is positive. This creates the shallow valley where our vacuum sits. But as you increase energy, quantum corrections start to matter. Virtual particles popping in and out of existence affect the field's behavior. Around 10 to the 11 GeV, the Higgs self-coupling turns negative. The valley becomes a hilltop. At these energies, the Higgs field strongly prefers to roll downhill toward a different value, the true vacuum value. This means that if you could somehow give the Higgs field enough energy to reach this scale, it would immediately begin rolling toward the true vacuum. Not through quantum tunneling, but through classical motion over the energy barrier. The most disturbing evidence comes from black hole physics. In 2018, theorists at the Max Planck Institute calculated what happens when a black hole evaporates through Hawking radiation. As a black hole loses mass, its temperature increases. A solar mass black hole has a temperature of just 60 nanokelvin, far too cold to matter, but as it shrinks, it gets hotter. In the final moments before a black hole completely evaporates, its temperature reaches the Planck scale, about 10 to the 32nd Kelvin. At these temperatures, particle energies reach 10 to the 19 GeV, well into the range where the Higgs field becomes unstable. The researchers found that an evaporating black hole could create conditions that destabilize the vacuum locally. The bubble of true vacuum would nucleate at the black hole's location and expand outward at light speed. This means that every black hole in the universe is potentially a time bomb. As soon as one evaporates completely, which takes about 10 to the 67 years for a solar mass black hole, it could trigger the end of everything. Recent observations reveal patterns in the cosmic microwave background that hint at vacuum instability. In 2020, the Planck satellite team analyzed temperature fluctuations in the CMB with unprecedented precision. They found anomalies at the largest angular scales, subtle patterns that don't quite match the predictions of standard inflation theory. Some theorists propose that these anomalies could be signatures of vacuum transitions in the very early universe. Perhaps our observable universe nucleated as a bubble of false vacuum during an earlier transition from a different vacuum state. If true, this would mean we're living inside a bubble that's still expanding. The bubble wall might be beyond our observable horizon, but it exists, moving outward at light speed, converting whatever lies beyond into our vacuum state. This interpretation remains speculative, but it demonstrates how vacuum decay connects to observational cosmology in ways we're only beginning to understand. The evidence extends beyond particle physics into the realm of quantum gravity. String theory, the leading candidate for a quantum theory of gravity, predicts the existence of a landscape of possible vacuum states. Not just 2 or 3, but perhaps 10 to the 500 different configurations, each with different physical constants. In 2003, Leonard Susskind at Stanford proposed that our universe might be just one bubble in an eternally inflating multiverse, where different bubbles nucleate with different vacuum states. Each bubble is a universe with its own physical laws. This landscape of possibilities means that vacuum decay isn't just possible, it's inevitable somewhere. In the vast multiverse, bubbles constantly nucleate, expand, collide, and spawn new bubbles. Our universe would be one temporary bubble in an endless cosmic foam. The question isn't whether vacuum decay happens, but whether it's happened here or will happen here within our cosmic horizon. The scientific theory that ties everything together is quantum field theory in curved spacetime, the synthesis of quantum mechanics, special relativity, and general relativity. According to quantum field theory, what we think of as empty space isn't truly empty. It's filled with fields: the electromagnetic field, the Higgs field, the quark fields, and others. These fields exist everywhere, at every point in space, constantly fluctuating due to quantum uncertainty. Each field has a ground state, the configuration with lowest energy. We call this ground state the vacuum. But quantum field theory permits multiple vacuum states, like valleys at different elevations on a landscape. The Higgs field is special because its vacuum value determines the masses of other particles. Change the Higgs vacuum and you change particle masses. Change particle masses and you change chemistry, nuclear physics, gravity, everything. Leading physicists have competing interpretations of what vacuum metastability means for our universe. Frank Wilczek at MIT argues that metastability shouldn't concern us. The timescales are so long, 10 to the 100 years or more, that vacuum decay is effectively impossible. The universe will die through heat death or big rip long before vacuum decay becomes relevant. Steven Weinberg offered a different perspective. He suggested that the metastability of our vacuum might be anthropically selected. In the multiverse of all possible vacua, only those lasting long enough for intelligent life to evolve can be observed. We find ourselves in a metastable vacuum not because it's common, but because stable vacua and unstable vacua both fail to produce observers. A third view, championed by theorists at Perimeter Institute, treats vacuum decay as inevitable. Given infinite time and infinite space, every possible quantum event will eventually occur. Vacuum decay is possible, therefore it will happen. The question is only when and where. This forces us to reconsider fundamental assumptions about the universe's fate. Traditionally, cosmologists considered three possible ends: the Big Freeze, heat death as the universe expands forever; the Big Crunch, gravitational collapse; or the Big Rip, accelerating expansion tears everything apart. Vacuum decay adds a fourth possibility: sudden, total conversion to a different vacuum state. Unlike the other scenarios, which unfold over billions or trillions of years, vacuum decay would be instantaneous from our perspective. The transition wall approaches at light speed. We can't see it coming. One moment, normal physics. The next moment, different physical laws, different particle masses, different fundamental constants. No warning, no time to prepare, no possibility of survival. Some cosmologists find this scenario oddly comforting. If the universe must end, a quick, painless annihilation might be preferable to the slow freeze of heat death or the violent chaos of the Big Rip. Ongoing research is refining our understanding of vacuum stability with increasing precision. The High Luminosity Large Hadron Collider, scheduled to begin operations in 2029, will measure the Higgs boson mass and couplings with unprecedented accuracy. Current measurements have uncertainties of about 0.2 GeV. The HLLHC aims to reduce this to 0.02 GeV, 10 times better precision. This matters because vacuum stability is exquisitely sensitive to the Higgs mass. A small change in the measured value could shift our universe from metastable to stable, or from metastable to unstable. We're genuinely unsure which side of the boundary we're on. Future colliders, the proposed International Linear Collider in Japan, the Circular Electron-Positron Collider in China, or the Future Circular Collider at CERN, could probe even higher energies, potentially reaching energy scales where vacuum instability becomes directly observable. Recent breakthroughs suggest new ways to test vacuum decay physics. In 2022, physicists at MIT proposed using quantum simulators, artificial systems that mimic quantum field behavior, to study vacuum decay in laboratory settings. By creating analog vacuum states in ultra-cold atomic gases or superconducting circuits, they hope to observe tunneling dynamics directly. These experiments wouldn't trigger actual vacuum decay, they operate at far too low energies, but they could verify the quantum mechanical predictions that underlie vacuum decay calculations, increasing our confidence in the theoretical models. Gravitational wave observatories might also provide evidence. If vacuum decay bubbles have nucleated in the distant universe, the collisions between expanding bubbles would produce gravitational waves. The next generation of detectors, LISA, Einstein Telescope, Cosmic Explorer, might be sensitive enough to detect these signals. What technologies might help solve remaining mysteries? Advanced particle accelerators could probe the Higgs field behavior at higher energy scales, mapping the landscape of possible vacuum states more completely. Each measurement constrains the theory, narrowing the range of possibilities. Precision cosmology using future space telescopes like the Nancy Grace Roman Space Telescope or the proposed LUVOIR mission could detect subtle signatures of vacuum transitions in the early universe. Patterns in the distribution of galaxies or in the cosmic microwave background might reveal whether our universe nucleated from a vacuum decay bubble. Quantum computing might enable detailed simulations of quantum field theory that are currently impossible. Calculating vacuum decay rates requires accounting for all possible quantum paths, an exponentially difficult problem for classical computers. Quantum computers could handle this naturally. What this means for us goes beyond abstract physics. Vacuum decay reminds us that the universe we inhabit isn't necessarily permanent. The physical laws we rely on, gravity, electromagnetism, the nuclear forces, might be temporary features of a metastable vacuum state. Reality itself could be provisional. This challenges the assumption that the universe exists in its most fundamental configuration. We might be living in an excited state, a temporary arrangement that will eventually settle into something more stable. Life, intelligence, everything we know might be possible only in this temporary phase. Yet there's something profound about our position. We exist at exactly the energy scale where physics becomes interesting. Too high and the vacuum is unstable. Too low and nothing interesting happens. The metastability of our vacuum might be precisely what enables the rich complexity of chemistry, biology, and consciousness. We are balanced on a knife edge, and that balance might be what makes existence meaningful. The most profound implications emerge when we consider the anthropic dimension of vacuum stability. The fact that we exist to ask these questions constrains what we can observe. We can only find ourselves in a universe that permits observers to exist. This is the anthropic principle. Applied to vacuum decay, this principle suggests something remarkable. Among all possible vacuum states in the landscape of string theory, most would be hostile to life. Either completely stable but boring, with no interest in chemistry, or wildly unstable, decaying too quickly for complexity to evolve. We observe a metastable vacuum because that's the only kind of vacuum where observers like us could exist. It's stable enough to last billions of years, long enough for stars to form, planets to cool, life to evolve, but not so stable that we're stuck in the absolute ground state. This implies that consciousness itself might depend on living in a temporary universe. What the evidence suggests about reality itself challenges everything we thought we knew. If our vacuum is metastable, then the physical constants we measure, the electron mass, the strength of gravity, the speed of light, aren't fundamental features of nature. They're environmental properties of our particular vacuum state, no more fundamental than the temperature of air or the pressure of water. In a different vacuum state, electrons might be heavier or lighter. Gravity might be stronger or weaker. Light might travel at a different speed. The fine structure constant, which governs electromagnetic interactions, could have a different value. This means that asking, why do the physical constants have the values they do, might be like asking, why is it 20 degrees Celsius today? It's not a question about fundamental physics, but about environmental conditions. The constants aren't constant across the multiverse. They're local properties of our vacuum bubble. Unsolved mysteries and paradoxes remain. The biggest question, is our vacuum metastable or unstable? Current measurements can't definitively answer this. We're in a gray zone where theoretical uncertainties and experimental limitations overlap. If metastable, how long will it last? The calculations suggesting 10 to the 100 years rely on assumptions about quantum gravity that we can't verify. The true lifetime could be longer or shorter by many orders of magnitude. Another puzzle, what triggers vacuum decay? Is it purely random quantum tunneling, or could high-energy events catalyze it? Could cosmic rays, particle collisions, or black hole evaporation serve as triggers? Perhaps the deepest mystery, if vacuum decay is possible and the universe is infinite, why hasn't it happened yet? In an infinite universe, every possible quantum event should already have occurred. By rights, a vacuum decay bubble should have nucleated somewhere, expanded at light speed, and consumed the entire cosmos long ago. The fact that we exist suggests either the universe is finite, or we're incredibly lucky, or there's something wrong with our understanding of vacuum decay physics. Multiple possible futures emerge based on the evidence. In one future, better measurements show our vacuum is actually stable. The Higgs mass, when measured with sufficient precision, places us in the stable region. The universe is safe from vacuum decay. This would be comforting, but would raise new questions about why our vacuum happens to be stable when most possible vacua are not. In another future, we confirm metastability, but develop a deeper understanding of quantum gravity that reveals vacuum decay is impossible for reasons we don't yet understand. Some unknown physics at the Planck scale prevents vacuum transitions, protecting our universe indefinitely. In yet another future, we detect evidence of vacuum decay occurring elsewhere in the universe, a distant bubble nucleating and expanding toward us. Observing it coming wouldn't save us, but it would answer the question of vacuum stability definitively. We would know our time is limited, measured by the speed of light and the bubble's distance. The most unsettling possibility, vacuum decay could happen without any advance warning, anywhere, anytime. The universe is metastable, decay is possible, and we're simply living in the period before it occurs. Our existence is temporary by definition, and the end could come at any moment. We've journeyed from Coleman and Luccia's 1977 calculation through the 2012 discovery of the Higgs boson to the cutting edge of modern particle physics and cosmology. Along the way, we've seen that the stability of our universe hangs on the precise values of fundamental constants, particularly the Higgs mass and top quark mass. We've learned that our vacuum might be metastable, perched in a temporary configuration that could, through quantum tunneling, transition to a lower energy state. We've seen how this transition would propagate at light speed, rewriting the laws of physics and destroying everything in its path. We've explored how this connects to the anthropic principle, the multiverse, and the ultimate fate of the universe. We've seen that vacuum decay represents not just a theoretical curiosity, but potentially the final chapter in the history of everything that exists. Returning to our opening question with transformed understanding, yes, the universe might be sitting on the edge of catastrophic collapse. The physics is real, the mathematics is sound. The probability is non-zero. But probability isn't certainty. The timescales are genuinely astronomical, far longer than the current age of the universe, probably longer than the time until heat death. Vacuum decay is possible, but so unlikely that it might never happen within our cosmic horizon. Current scientific consensus holds that our universe is metastable but long-lived. The vacuum will probably last long enough for the universe to end through other means first: heat death as stars burn out and black holes evaporate, or the Big Rip as dark energy tears spacetime apart. Yet the possibility remains, a small but non-zero chance that somewhere, sometime, a bubble nucleates and everything ends instantly. What remains unknown exceeds what we've learned. We don't know the exact energy barrier protecting our vacuum. We can't calculate the true decay rate with confidence. We don't know if high-energy events can trigger decay or whether it's purely random. We haven't reconciled vacuum decay with quantum gravity or developed a complete theory of the multiverse. But there's something profound in this uncertainty. We exist in a universe balanced between stability and instability, a universe that's lasted long enough for stars to form, for life to evolve, for intelligence to emerge and ask these questions. We're temporary. The universe is temporary. Everything we know might rest on borrowed time. Yet here we are, thinking, exploring, understanding, making the most of whatever time we have. The universe might be metastable. Reality itself might be provisional. Existence might rest on a knife edge. But that edge is where we live, and it's beautiful. The universe is vast. The mysteries are endless. The journey continues. 5 times more abundant than all the atoms in the universe. Invisible, untouchable, passing through your body right now at hundreds of kilometers per second. And we have absolutely no idea what it is. Every star you see, every planet, every galaxy, every living thing, all of it represents just 15% of the matter in the universe. The other 85% is something else entirely. Something that doesn't interact with light, doesn't emit radiation, doesn't absorb energy. Something we can only detect through its gravitational pull on visible matter. We call it dark matter, and it's the scaffolding upon which everything else is built. Without dark matter, galaxies would fly apart, stars would drift into the void. The cosmic web of structure we observe throughout the universe simply wouldn't exist. Yet despite decades of searching with the most sensitive instruments ever built, we've never directly detected a single particle of it. What if everything we think we know about the universe, about gravity, about matter, about the nature of reality itself is fundamentally incomplete? What if the cosmos is constructed from something so alien to our experience that we lack even the conceptual framework to understand it? Today, we journey through evidence that reveals our universe is dominated by an invisible presence we can measure but cannot see, touch, or comprehend. Prepare yourselves. We begin. For 4 decades, Zwicky's discovery was largely ignored. Most astronomers dismissed his findings as observational error or mathematical mistake. The idea of invisible matter seemed too strange, too convenient. It felt like inventing something to fix an equation rather than discovering something real. Then came Vera Rubin. In the 1970s, Rubin was studying the rotation curves of spiral galaxies at the Carnegie Institution in Washington. She measured how fast stars orbit around galactic centers at various distances. According to Kepler's laws, the same laws governing planets orbiting the Sun, stars farther from the galactic center should orbit more slowly, just as Neptune orbits more slowly than Earth. But that's not what Rubin observed. Working with Kent Ford, Rubin measured the spectra of stars in the Andromeda Galaxy and dozens of other spirals. They used the Doppler shift, the change in light frequency caused by motion, to determine precise orbital velocities. The results were impossible to deny. Stars at the edge of galaxies moved just as fast as stars near the center. The rotation curves were flat, not declining. It was as if the galaxy's mass extended far beyond its visible edge, in a vast spherical halo of invisible matter. Rubin calculated that galaxies must contain at least 10 times more dark matter than visible matter. The luminous galaxy we see, the spiral arms, the glowing gas, the billions of stars, is just a small island floating in an enormous ocean of darkness. Here's an analogy. Imagine watching a carousel spin. The horses near the center and the horses at the outer edge all complete one rotation in the same time. This violates what we know about circular motion. The outer horses must be held by something we can't see, invisible arms extending beyond the visible carousel. Galaxies are those carousels, the visible stars are the horses, and dark matter is the invisible structure holding everything together. But here's where it gets truly strange. Rubin's observations revealed that dark matter doesn't just surround galaxies, it dominates them. The luminous matter, everything we can see, traces out where the dark matter is, like foam on ocean waves. The dark matter is the ocean. This meant everything we thought we knew about galaxies was wrong. We thought galaxies were collections of stars held together by their mutual gravity. In reality, galaxies are concentrations of dark matter that happen to collect visible matter within them. The stars, the gas, the planets, the life, all of it is incidental. The universe's true structure is written in dark matter. We just see the highlights. The discovery forced astronomers to reconsider the universe's composition from the ground up. Follow-up observations confirmed Rubin's findings in hundreds of galaxies. Every spiral galaxy observed showed the same flat rotation curve. Every elliptical galaxy required far more mass than its visible matter could provide. Every galaxy cluster moved as if filled with invisible matter. The evidence was universal. Dark matter wasn't a quirk of one or two strange systems. It was everywhere, fundamental, dominant. But the evidence forces us to confront an uncomfortable possibility. What if the matter we're made of, protons, neutrons, electrons, the building blocks of atoms, represents a tiny minority of the universe's substance? What if we're not just rare in space, but made of rare matter? The first independent confirmation came from gravitational lensing. In 1979, astronomers discovered a strange double image in the sky. Two quasars with nearly identical spectra appearing close together. It turned out to be a single quasar whose light was being bent around a massive foreground galaxy, creating two images. Einstein's general relativity predicts this effect. Mass curves spacetime, and light follows that curvature. A massive object acts as a gravitational lens, bending and magnifying the light from objects behind it. By measuring the degree of lensing, astronomers could calculate the total mass of the lensing object. And consistently, they found the same result. The total mass far exceeded the visible mass. The invisible mass, dark matter, was doing most of the lensing. Scientists discovered something extraordinary in the bullet cluster, a cosmic collision 3.7 billion light-years away. In 2006, NASA's Chandra X-ray Observatory observed two galaxy clusters that had passed through each other at speeds around 4,700 kilometers per second. The hot gas in each cluster, visible in X-rays, slowed down during the collision, like two clouds of steam colliding and mixing. But the galaxies themselves passed through mostly unaffected. Galaxies are mostly empty space, so they can interpenetrate without direct collisions. The remarkable discovery? Gravitational lensing maps showed that most of the mass wasn't where the gas was, it was where the galaxies were. The dark matter halos surrounding each cluster's galaxies had sailed through the collision barely interacting, separating from the gas. This provided direct evidence that dark matter is real, not just a mathematical fiction. It's actual matter that can be separated from normal matter. The bullet cluster showed dark matter and normal matter behaving differently in the same cosmic event. But this represents just one piece of a much larger puzzle hidden in the cosmic microwave background. The Planck satellite, launched in 2009, mapped temperature fluctuations in the CMB with extraordinary precision. These fluctuations, tiny variations in temperature across the sky, encode information about the universe's composition 380,000 years after the Big Bang. The data revealed something crucial. The acoustic peaks in the CMB power spectrum match theoretical predictions only if the universe contains approximately 26.8% dark matter, 4.9% normal matter, and 68.3% dark energy. This measurement is independent of galaxy rotation curves and gravitational lensing. It comes from the early universe, from physics operating billions of years before galaxies formed. Yet it confirms the same conclusion. Dark matter dominates normal matter by a ratio of about 5:1. The most remarkable discovery involves computer simulations of cosmic structure formation. In the 1980s and 1990s, cosmologists built sophisticated simulations modeling how matter clumped together under gravity from the nearly smooth early universe to the web-like structure of galaxies and clusters we see today. Simulations using only normal matter failed spectacularly. They produced a universe nothing like ours. Galaxies formed too late and too small. Large-scale structure never developed properly. The simulations couldn't reproduce reality. But add dark matter, specifically cold dark matter that moves slowly and clumps efficiently, and everything changes. The simulations produce structures remarkably similar to what telescopes observe. Galaxy clusters, cosmic voids, filaments connecting clusters all emerge naturally. The Millennium simulation, run in 2005, tracked the evolution of 10 billion dark matter particles through cosmic history. It reproduced the observed universe with stunning accuracy, from the distribution of galaxy clusters down to details of individual galaxy halos. This success is powerful evidence. The dark matter hypothesis isn't just fixing equations, it's making successful predictions about cosmic structure. Now we venture into stranger territory. What is dark matter made of? The leading hypothesis involves WIMPs, weakly interacting massive particles. These theoretical particles would have masses 10 to 1,000 times heavier than protons and interact only through gravity and the weak nuclear force. WIMPs arise naturally from supersymmetry, a theoretical extension of particle physics. Supersymmetry predicts that every known particle has a heavier superpartner. The lightest supersymmetric particle could be stable and abundant enough to account for all dark matter. The appeal is elegant, solving two problems with one theory. Supersymmetry addresses mathematical issues in particle physics, while simultaneously providing a dark matter candidate. But decades of searching have found nothing. The Large Hadron Collider has looked for supersymmetric particles at energies up to 13 trillion electron volts. No evidence. Underground detectors shielded from cosmic rays have looked for WIMPs colliding with atomic nuclei. No signal. The most disturbing evidence comes from ultra-faint dwarf galaxies. These tiny galaxies orbiting the Milky Way contain just a few thousand stars, but show mass-to-light ratios exceeding 1,000 to 1. They're almost pure dark matter, with a sprinkling of stars, like tiny drops of light in vast oceans of darkness. Studies of these dwarfs reveal something unexpected. The distribution of dark matter doesn't match predictions. Simulations predict dark matter should be densest at galactic centers, forming sharp cusps, but observations show smooth cores instead. This is the cusp-core problem, and it challenges the cold dark matter model. Either our simulations miss important physics, or dark matter behaves differently than we think. Perhaps dark matter particles can collide with each other occasionally, transferring energy and smoothing out the density peaks. This requires dark matter to have self-interactions, something pure WIMPs don't have. Recent observations reveal patterns that hint at dark matter's complexity. In 2014, astronomers detected an unexplained X-ray signal at 3.5 kiloelectron volts coming from galaxy clusters and the Andromeda Galaxy. The signal's energy doesn't match any known atomic transition. One possibility? Dark matter particles decaying into photons. If real, this signal could be our first direct detection of dark matter beyond its gravitational effects. The energy suggests dark matter particles with masses around 7,000 times the electron mass, consistent with some theoretical models. But the signal is faint and difficult to confirm. Other telescopes have looked for it with mixed results. Some find weak evidence, others see nothing. The debate continues. The evidence extends beyond particle physics into the realm of modified gravity theories. Some physicists propose we don't need dark matter at all. Instead, perhaps gravity behaves differently on galactic scales than Einstein's theory predicts. MOND, modified Newtonian dynamics, proposes that gravity becomes stronger at very low accelerations, like those experienced by stars at the edges of galaxies. MOND successfully reproduces galaxy rotation curves without invoking dark matter. But MOND struggles with galaxy clusters and gravitational lensing. It can't explain the bullet cluster or the CMB acoustic peaks. Most physicists consider it unlikely to be the full answer. Still, MOND reminds us that dark matter exists isn't the only possible interpretation. We might be misunderstanding gravity itself rather than missing matter. Or perhaps reality involves both new matter and modified gravity. The universe might be more complex than either explanation alone suggests. The scientific theory that ties everything together is the lambda CDM model, lambda cold dark matter cosmology. This model describes the universe as containing three main components: normal matter, 4.9%, cold dark matter, 26.8%, and dark energy, represented by lambda, 68.3%. CDM means that dark matter is cold, moving slowly compared to light speed, allowing it to clump into structures. The model successfully explains an enormous range of observations: galaxy rotation curves, gravitational lensing, the CMB power spectrum, large-scale structure formation, and the universe's expansion history. It's the standard model of cosmology, as well tested as the standard model of particle physics. But like all scientific theories, it's incomplete. It tells us dark matter exists and how much there is, but not what it is. It's a framework waiting to be filled in with specific. Leading physicists have competing interpretations of dark matter's nature. Catherine Fries at the University of Texas champions dark stars, the idea that dark matter annihilation in the early universe powered a generation of exotic stars. These dark stars could have seeded galaxy formation and might still exist in the early universe, visible to next-generation telescopes. Lisa Randall at Harvard explores the possibility of dark sectors, entire parallel worlds of dark particles interacting through dark forces. Just as normal matter includes protons, neutrons, electrons, photons, and complex atoms, dark matter might be equally complex. We'd be observing only the gravitational effects of an entire shadow chemistry. Dan Hooper at Fermilab investigates axions, ultralight particles originally proposed to solve problems in quantum chromodynamics. Axions could be produced copiously in the early universe, and today exist in vast clouds permeating galaxies, with densities of billions per cubic centimeter. Each interpretation has different experimental signatures and different implications for how we search. This forces us to reconsider fundamental assumptions about matter and forces. We've long believed that the matter we're familiar with, atoms built from quarks and electrons, represents the basic stuff of reality. Dark matter suggests this view is parochial. The familiar periodic table, chemistry, nuclear physics, all of it describes the minority constituent of the universe. The majority is something else, something that doesn't participate in electromagnetism, so it doesn't emit light or interact chemically. Something that experiences gravity, but possibly other forces we've never encountered. If dark matter has its own forces and interactions, there might be dark atoms, dark chemistry, even dark complexity. Not dark life, that's pure speculation, but at least rich structure beyond simple particle clouds. We might be living in a universe far stranger and more diverse than we imagine. A universe where our kind of matter is a rare edge case, and the dominant form of matter follows completely different rules. Ongoing research is pursuing dark matter through multiple strategies simultaneously. Direct detection experiments deep underground use tanks of liquid xenon or other materials, waiting for a dark matter particle to collide with an atomic nucleus. The largest current experiment, Luccia in South Dakota, uses 7 tons of liquid xenon and can detect collisions producing energies as small as a few keV. These experiments operate deep underground, 1,600 meters below the surface for Luccia to shield against cosmic rays. They cool detectors to near absolute zero to minimize thermal noise. They use the purest materials ever manufactured to eliminate radioactive contamination. And so far, after decades of progressively more sensitive searches, they've found nothing definitive. The lack of signal is ruling out vast swaths of theoretical parameter space, telling us what dark matter isn't, even if we can't yet discover what it is. Recent breakthroughs suggest new search strategies. The ADMX experiment at the University of Washington searches for axions using a high-powered magnet and sensitive radio receivers. If axions exist and pass through a strong magnetic field, they should convert into photons at specific frequencies related to the axion mass. ADMX has been operating for over 2 decades, gradually scanning through possible axion masses. In 2018, they reached sensitivity capable of detecting even pessimistic axion models, entering territory where discovery becomes plausible. Meanwhile, the Fermi Gamma-ray Space Telescope searches for signals of dark matter annihilation in space. When dark matter particles collide, they should annihilate into gamma rays. The center of our galaxy, dwarf satellite galaxies, and galaxy clusters are prime hunting grounds. Some tantalizing hints have emerged: excess gamma rays from the galactic center, unusual signals from dwarf galaxies, but nothing definitive. The challenge is distinguishing dark matter signals from astrophysical backgrounds like pulsars and supernova remnants. What this means for us extends beyond academic curiosity. Understanding dark matter means understanding the universe's structure and evolution. It affects the formation of galaxies, the distribution of matter, the ultimate fate of cosmic expansion. Every question about cosmic history involves dark matter. It also tests the limits of human knowledge. We're forced to study something we cannot see, touch, or directly measure. We must infer its properties from subtle gravitational effects and missing mass in cosmic accounting. This develops new ways of thinking about evidence and inference. We learn to trust mathematics and careful reasoning even when direct observation is impossible. These cognitive tools apply far beyond physics, to economics, psychology, any field dealing with invisible influences and indirect evidence. Dark matter reminds us that reality extends beyond human perception. The universe contains more than our senses reveal. Understanding it requires intellectual tools, mathematics, theory, careful reasoning that transcend direct experience. The most profound implications emerge when we consider what dark matter reveals about our place in the cosmos. We're made of atoms, protons, neutrons, electrons. These particles comprise just 15% of the universe's matter. The other 85% is fundamentally different stuff that doesn't share our physics. This means we're not just cosmically rare in terms of location or timing. We're made of rare matter. The material composing our bodies, our planet, our stars represents a minority constituent of reality. If consciousness requires the complexity enabled by chemistry, and chemistry requires electromagnetic interactions, then consciousness might be fundamentally impossible for dark matter. The vast majority of the universe's matter might be forever unconscious, unable to experience or reflect on its own existence. We occupy a strange niche, rare matter capable of understanding, observing, questioning. The universe's dominant component might be forever mute and blind, while we, the minority, achieve awareness. What the evidence suggests about reality itself challenges our intuitions. Dark matter demonstrates that the universe is fundamentally invisible to us. The majority of substance passes through our bodies constantly without interaction, We're transparent to it. It's transparent to us. We share space but might as well inhabit different realities. This suggests a layered universe, multiple substances coexisting in the same space, each responding to gravity but otherwise operating independently. Our electromagnetic reality and dark matter's gravitational reality overlap without touching. Could there be other layers we haven't discovered? Other forms of matter responding to forces we haven't encountered? The universe might be more crowded than we imagine, filled with substances and forces beyond our current understanding. The fact that we discovered dark matter at all, through careful observation and reasoning, suggests we can eventually understand it. But it also reveals how much remains hidden. If 85% of matter went unnoticed until the 20th century, what else are we missing? Unsolved mysteries and paradoxes remain. The biggest question: what is dark matter? After 90 years since Zwicky's discovery, we still don't know. It could be WIMPs, axions, primordial black holes, sterile neutrinos, or something nobody has imagined yet. Another puzzle? Why is there exactly 5.5 times more dark matter than normal matter? This ratio seems arbitrary. No known theory explains why these two very different kinds of matter should exist in similar amounts. The missing satellites problem. Simulations predict large galaxies like the Milky Way should have thousands of small dark matter halos orbiting them. We see only a few dozen dwarf galaxies. Where are the rest? Are they dark, pure dark matter without stars? Or is something wrong with our models? Perhaps the deepest mystery? Did dark matter enable life? Without dark matter, galaxies wouldn't form properly. Stars wouldn't organize into stable structures. The universe would be a sparse, chaotic place. Life requires stable environments, planetary systems in orderly galaxies. Dark matter provides that stability. We might owe our existence to invisible scaffolding we've only recently learned to detect. Multiple possible futures emerge based on current evidence. In one future, we detect dark matter particles directly within the next decade. Experiments finally register clear signals revealing dark matter's mass, interaction strength, and properties. This opens a new chapter in physics, understanding dark matter's dynamics, searching for dark forces, perhaps discovering dark complexity. In another future, dark matter remains elusive, but we map its distribution with exquisite precision. Gravitational lensing surveys and galactic dynamics reveal exactly how dark matter clumps and flows, even if we never identify individual particles. We understand dark matter through its effects, much as we understood atoms before seeing them directly. In yet another future, experiments rule out all simple dark matter candidates, forcing radical revision of our theories. Perhaps dark matter is far more exotic than WIMPs or axions. Perhaps it involves extra dimensions, quantum gravity effects, or physics beyond our current frameworks. The most revolutionary possibility, we discover dark matter has rich internal structure. Dark atoms, dark molecules, dark chemistry. An entire shadow world operating by different rules but sharing our space. This would transform our understanding of what the universe contains and hint at realities we've barely imagined. We've journeyed from Fritz Zwicky's 1933 observation of impossible galaxy velocities, through Vera Rubin's revolution in the 1970s, to today's cutting-edge searches in underground laboratories and space observatories. Along the way, we've seen evidence from rotation curves, gravitational lensing, the cosmic microwave background, and computer simulations, all pointing to the same conclusion. Dark matter is real, it dominates the universe, and we still don't know what it is. We've learned that the visible universe, everything we see, everything we're made of, represents just the tip of the cosmic iceberg. The vast majority lies hidden, detectable only through gravity's subtle pull. We've seen how dark matter shaped cosmic history, enabling galaxies to form, stars to ignite, planets to cool, and life to emerge. Without it, the universe would be a vastly different and probably empty place. Returning to our opening question with transformed understanding, yes, dark matter is passing through your body right now.
billions of particles every second, interacting so weakly you never notice. You're transparent to it. It's transparent to you. Current scientific consensus holds that dark matter consists of unknown particles produced in the early universe, distributed in vast halos surrounding galaxies and comprising 85% of all matter. But the exact nature remains uncertain. We're still searching. What remains unknown exceeds what we've learned. We don't know dark matter's mass, interaction strength, or whether it has internal structure. We don't know if there's one type or many. We don't know if it's connected to other unsolved mysteries like dark energy or cosmic inflation. But we're closer than ever. Every experiment constrains the possibilities. Every observation refines our models. Every year brings new searches with unprecedented sensitivity.
Dark matter reminds us that the universe is stranger than we imagined, that most of reality operates beyond human perception. That understanding requires intellect, mathematics, and careful reasoning rather than direct experience. It shows us that we're made of rare substance, the minority of matter that can organize into complexity, chemistry, consciousness. We're cosmic outliers, using our brief moment of awareness to study the invisible foundations supporting our existence. In the vast, dark ocean of the universe, we're tiny, luminous islands asking questions about the depths below. The universe is vast. The mysteries are endless. The journey continues.
Dark matter reminds us that the universe is stranger than we imagined, that most of reality operates beyond human perception, that understanding requires intellect, mathematics, and careful reasoning rather than direct experience. It shows us that we're made of rare substance, the minority of matter that can organize into complexity, chemistry, consciousness. We're cosmic outliers, using our brief moment of awareness to study the invisible foundations supporting our existence. In the vast dark ocean of the universe, we're tiny luminous islands asking questions about the depths below. The universe is vast. The mysteries are endless. The journey continues.